do I have? And BTA. Sorry, guys. I thought I was going to be able to use the other program, but 6. OF6VI. Okay, so let's get this downloaded. What doesn't it like about those cards? Faulted, you say? Fault. Why electronic key mismatching? Well, that's fun. Revision 3.02. Oh, okay. 3.09. Fix that. Your problem. Product type 76, revision code 302. V16. Sure. Wonderful. That's great. So again, recoverable faults are ones that you can actually recover, and then so without it halting the logic. Unrecoverable faults cannot be cleared by the fault handling routine. So these faults are serious, corrupt controller memory, power, power faults. So they can't be cleared. And sometimes they'll actually require a download to fix. So if you corrupt your processor, obviously it's going to stop running and you'll have to download a new copy of the code or set up automatic recovery through an SD card if you have that. So recoverable stuff, negative presets and timers, pointing to an element that doesn't exist in an array. So if you remember last week when I had an array and a counter doing some indirect addressing, and I went to write to an element at the end of the array, the processor faulted. That's a recoverable one. Unrecoverable ones, again, problems. So like Addy said, damage to the chassis. So as long as it's not a specific card that you're trying to ignore, if there's actually damage to the processor, loss of power to parts of the processor, pointing to an element, and then corrupt memory within the controller that might need to be replaced. I feel like I'm repeating myself. So based on knowing you can recover some of these faults, it's possible to write some custom fault handling routines that will reset logic in the event that you know something is going to happen. So if you have a persistent issue, you have cards that are faulting, obviously the best thing to do, like we saw here with this card, I had to disable the keying to prevent a fault from happening. If I had left the compatible keying on and the card stayed faulted, and under connection, we major fault. So you can turn this off if you want. So you can turn off major fault if you've lost connection. But with that faulted card and that enabled, we've faulted the controller. So we don't have any fault handling set up right now. So the controller stops, code's no longer executing. So obviously the best fix is to try to eliminate the condition that's causing these faults. So if you have a faulty card and you have access to spare cards, swap the card out to something that's working. If it's 3 weeks to order one in because the supply chain is screwed up right now, for example, I think we are 32 weeks out on a VFD for a capital project. That's most of a year. So if you don't have spares on your shelf right now, you could have to fight fires and band-aid things like writing this fault recovery logic. If you've got a card that you can allow to fault, well, turn it off, hit OK. We can clear the fault and we can continue on our way. it'll run with this error here. So you can see we've got a flashing IO not responding issue. If this were still allowing all of your inputs to work, you could let this run like this. If any of your inputs were not working properly, that might be something you would need to address. If you can't trust your IO cards, you can't trust your process. So minor faults versus major faults. Minor faults will not force the controller to stop scanning. The controller will stay in run mode, so it won't. This won't go red. The fault light on the front of the controller won't flash red. The PLC will operate normally, but your minor faults will show up in this list. So minor faults are some IO faults, low battery faults. You can turn some of these on. We can see a low battery fault would show up in here. Math errors would show up in here if you did something like divide. So doesn't like that, but it doesn't fault the controller. It'll just show up as arithmetic errors here. So it's not going to do anything in your major faults, but minor faults can impact the controller, could slow it down. And then this error, like it's going to keep filling up. That date's way off. So they don't cause, again, minor faults don't cause the process to fault, but it's still something's wrong. Your code's not working the way you intended it to. You're doing something that the PLC doesn't like. Newer controllers, like if you were to have done this on an old MicroLogix before some of the later firmware updates, this would absolutely fault the controller. It couldn't handle this math error. Some older controllers can't do it either. So you even have to, if you were doing division inside of a compute block, and you could potentially run the risk of your divisor being equal to exactly 0 at some point, you could just fault the controller randomly. So you'd have to modify your math so that you were never dividing by 0. So if anything in your divisor were equal to 0, you might want to prevent the compute from executing. So I've done that before, where you'd have a compute and then an NEQ. So as long as your divisor or whatever in your divisor, which might make something equal to 0, is not equal to 0, then you could execute your compute. Something to just think about when dealing with math operations. So arithmetic overflow, so dividing by 0 or integers being greater than 32,767. Wall clock time is out of range. So remember the get system value and set system values we used in the past. If you were to set the date to something out of range, that would be a minor fault. Controller temperature approaching its operating limit would be a minor fault. If you have a missing or dead battery is a minor fault. So we can now look at some fault handling routines. So there's two different types of fault handling routines. There's two spots that you can do them. So you can either do them here. And we'll call this task. Put that in the main program. And then when you configure your main program, you can configure your main routine, and then you can point the fault handling at the fault handling routine. So these are then program or task specific handling routines. And then you'll also have one up here, which is controller wide. We can't edit this one offline. So this one we can edit online. We would have to go offline to add a new program, and then so this one will run if there's faults inside only the main program. And then if you had a second task, periodic task, so if you have a fault handling routine set up for your main program, but your major fault occurs in your periodic program, the one that would catch your periodic program fault would be your controller tag, not this one. So this will only work within the main program, and there can be only one fault handling routine, one set of ladder logic inside each program. So does anybody remember, I know we talked about this, what's special about the fault handling task, the fault hand inside the program? It only runs once. Yeah, so it will execute top to bottom a single time. So if you want to use it to capture data, to log data, you have to make sure you get your order of operations right. So the example that we're using here is we're going to get a system value program. Program attribute name. We want a major fault record. And then it is 11. And we have our new tag, which is it didn't. 11. So the GSV, so the major fault record for the GSV spits out an array of dints. And why did that work? Oh. So on a fault, we get system value, the program main fault, and let's download this. We'll go back up to main routine. We'll add in okay. So we have a timer. So one of the major fault ones that's easy to do is a negative preset for a timer and then trigger it to run. So that faulted the controller. If we go over the fault handling routine, we can get information from it. So it's spit out their tags. It's spit out a whole bunch of information in here for us. So what is that information? I can hear you asking. So element 0 and element 1 are least significant least significant and most significant digits of the CTS, the coordinated system time. So that has to do with the timekeeping of the controller. And then element 2 is your fault code and fault type. So they'll have to be broken into binary and then converted to 2 words. So we've got oh goodness. Oh, 100. Right. Yep. Did this update? Oh, it's a silly VM. And the other one is 100010. All right. 00010. So when we break that code here into its two words, we've got 100010, which is 34. And over here, we've got 100 and 4. So if we go up to here, we can see we've got a code 34 type 4, which is your fault code. So we know that is, sorry to flip between all of these documents. It's kind of a dizzying for me too. So again, we've got our fault code, our fault type, and then the last 8 words are fault specific information, which you can look up. So we can see 34 and 4. So if we wanted to program to have this not do anything, one, you can either clear it here, the manual way, put it back and run. Oh, and it faults right away because I left that on. So since we know what we wanted to clear, we could then go move 0 to set system value program, main program fault. So if we execute this code, this isn't happy because that value's bogus, but the code, this is constantly writing. So you can see, but we're still in run mode. So we know this condition was coming. This is a bad one to program around, but you could, let's say you haven't configured your HMI routine to limit what your set points are. So I've seen some pretty terrible inputs for there's a piece of software called Wonderware, and when you pull it up, it would look, your entry would look something like a calculator. So you could punch in a set point of 1.015. But if the operator were to accidentally press, like, let's say they wanted to put in 0.15 and they actually went -25 and entered a negative value in, and then just hit enter, if you don't have a check in place and you've programmed it so they write directly into your timer set point, you could fault the controller. I've even seen I've even seen some data entry fields where if you were to, for whatever reason, type in like 2E35 into an integer, that'll fault the controller. That'll fault some controllers because 2E35 is scientific notation for a very large number, and that'll overflow any integer. So there are cases where you might need to enter this in if you have a bad interface where people keep entering in values that'll fault your controller. Heck, like, I don't want to say a lot of people will do it, but there are some machine operators I've met who they don't care if the machine's running or not. They get paid by the hour, not by the piece. So if they find a neat way to get a 20-minute break, they'll hit -25 on their unit, and then lights flash and maintenance comes out to fix the machine, and they don't care. So in an instance like that, maybe you do have to program around around that. Not ideal. So with this rung, when you have this set up, that it's just kind of spamming 0 into this record, it's clearing. And again, that's the fault record. If you remember from this document over here, this document. So you're kind of tricking the PLC where we get the system value, and then before the PLC essentially has a chance to read that it's faulted, we're zeroing it out. So we're kind of cheating. So it's a good idea to kind of cater these type of mass resets for the condition that you're looking for. So instead of just going move and then set the system value, what you might want to do is evaluate. So EQU. So if you know you have a couple of system faults, so if you have main program fault records 2 is equal to what was, if anybody remembers that value for 2. Oh, I'll have to fault it again. Oops. No. Really? We wrote it to 0. So now you can cater. Yeah, 3-4 was the binary or the decimal kind of conversion, but the I can't really enter that in. I mean, I guess I could have entered it in as a binary entry, but the decimal place. But thank you. You got that. Bonus points. So now, because we've catered it specifically for this fault, we can clear this fault if it occurs. But if there's another fault, that one will go through. So now, like Addie was saying, that won't be a program fault. What's another? Whoa.
Hey, Ryan.
Hi. Hello.
So, sorry, quick question.
Yep. Shoot.
So I see that we are doing a move function to move the zero value into the fault record array, but why are we using a system set value?
Because if we don't push it back, okay, so this major fault records attribute, that's part of the system. So if I were to delete this set and then run this, it'll still fault. So what's happening here is we've done something in the logic and we've faulted the controller. So this main routine knows the fault just happened. So in a last ditch effort to try to circumvent the impending end of the world, I'm being dramatic, if you can't tell, it's going to run its fault handling task, and it's going to do it once as a last gasp. So it's going to, for what we're doing, we're going get system value, and essentially we're taking the system value out, and here we're looking at the fault record, and then we're going to erase the fault record and then replace the system value. So when we use the set system value, it's like the main program has the record that we're going to fault it, and on the way to delivering it to the controller itself, somebody like erased the information, so the controller doesn't have a chance to fault. But if you don't set it back into it, it doesn't, it won't clear it. Does that make sense?
Okay.
Does
So it's
it?
almost like even though we are doing a move function, we need to make sure for fault handling, you need to set that value. Is that one way of looking?
Exactly. So it's like the execution of it. We're modifying the code, but if we don't output it back into the system value, the system's just going to run based on the logic that was executed.
Okay, that makes sense.
Okay, good. I thought I might butcher that one. And you can't do that when you're online. No. Oh. So then here, if we, we'll do it like this. I'm gonna go with int real dent. Five. Here. So here. value. So this, if you remember, I just made this dint is only 5 dints long. Yeah, watchdog for another. Watchdog for another. Like for the other periodic task. Or even this guy. So I can trigger this. So we can write into the 5th value, no problem, or the 4th value. But once we get to actual 5 here, well, that doesn't exist. So we've got another fault condition. So even though this executed once, it was only catered to faulting based on that other code. So if we go back into here, take a look at monitor tags, and we see 2 is this guy. I'll copy him to my clipboard. There. Back here. Monitor tag. Binary. So now again, we've got there's a 4, and then the other one was a what? Standard program. Binary. 1, 2, 3, 4. URA 101. So we've got a 20. So type of 20 and 4. We go back in here. We've got a 20 and 4. Can be trapped by fault routine, array subscript too large, or control data type positive, negative length. So there are any number of, where'd they go? Where'd they go? Minor fault codes. So inside this week's reading material, you have a PDF, which is pulled from Rockwell's website, whether it's their knowledge base or online. There's tons and tons of these for troubleshooting. And if you want to search major and minor fault codes, you can see type 116 IO configuration fault, 140s, 60s, watchdog timer expired. So all of these are going to trigger you, trigger inside the logic a different fault code. Major faults, minor faults will show up differently. So you can try to program around some of them. So we can add this in. Clear faults. Add this one in and allow it to go. It'll restart again. And now it won't fault, even though it wants to. So we can see here, if we were to look at this value, if we could see it, it would very quickly be cycling between probably both of these since they're both active faults at the moment. This one's trying to write to a non-existent set point. And if we clear this, that fault will clear. Or if we turn both of these off, it will clear. Another thing that's nice to run here is you can actually so oh, interesting. It only works once, eh? That clears? Oh yeah. Okay. I don't know why I thought that would work. I'm trying to remember how I managed to get another one to work to log the number of major faults. But I don't know if I have gotten that to work before. So I'm just looking through some of these notes to see if there's that's really it. So in the other routine, you can, let's see if I can make this fault. Oh, let it run to itself. Yeah. So I just set the watchdog for this controller, this periodic tag, to far shorter than I should have, which faults the controller. So the watchdog, if you remember, we covered these a few weeks back, is how long to give the controller to complete this task. And I just gave it far too little, even though there's nothing happening here, 0.1 of a millisecond. It didn't like that. Because I jumped to this program and then nothing happens over here. So it can't do anything. So it just gets mad. Anyways, this fault isn't in here. This guy's fine. Our fault routine didn't catch it. So if we would have had up here, we can actually do the same logic. It's just we need to go. So we actually got a 65542, which is a watchdog fault type 6.1. If we go back over to our troubleshooting guide, oh, where'd that go? 6.1. So a task watchdog expired, increase the task watchdog length, shorten the execution time, make the priority of the task higher, simplify higher priority tasks, or remove some code. So it gives you some ideas to modify your logic. And again, if we really wanted to, we could come in here. I think we can. I think this is one that we can do. No, that's unrecoverable. So even if we write to it, this one is not recoverable. Any questions? Concerns?
How are multiple faults stored in the fault code? Are they added together, or they're in a separate area of the fault code? Because we were looking for a specific number. However, as there's multiple faults, the number would be different, right? Or is there some
So
other storage space for it?
it's a good question. I've never really.
Do you have to take an account for every variation of multiple faults if you're looking for a specific fault, or what do you gotta do?
Yeah, that's a really good question, because if I run, so here, sorry, here you see your fault code for the IO card that I re-enabled. So if we wanted to, we could up here change. I'm not ignoring your question, Vincent. It really doesn't like that though. It does not like automatically clearing this fault. So that's supposed to be a recoverable one. There's something really wrong with that card. Really wrong. So multiple faults. So we have multiple faults here, right? So if we activate both of them, and then we come here, all we see changing because it's just too fast is that. So there's only one spot for it to be stored. So how would you do multiples? So we can see. Sorry. So, damn it. So you have no idea what I just did. Do you? Did you see what I did there? Is that confusing? Fuck. Sorry. This is how I troubleshoot. I just kind of randomly look at things. So one of the problems with your interface with your PLC is that reporting back to you is slow in comparison to what is actually happening in the controller. If you pay really close attention, maybe once in 1,000 scans, we'll see 2228, or maybe this one. It might pop up for a brief second, but it's happening so fast in the background that most of the time it's actually probably 0. So that can happen for a lot of different conditions. So if you think so, like if something's happening too quickly for you to actually see and capture and watch, what you can do is you can right click on the tag, and then you can either cross-reference monitor. Monitor's not going to show you much, but the important one here is trend. So it'll automatically open up a trend, and you can see here this blue line is actually the value, and you can see how quickly it's spiking. So it goes up and up, 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 down. So that time span of these spikes is actually the scan time of the controller, or at least the scan time of that fault routine. And this will run for a while. So you can stop it and then try to find what values it's actually storing. And it does, in this instance, it looks like it's never actually reaching the lower value, because all of these, I don't know if you can see that, are 2228228 E6. So it's actually 2.228228. And none of these spikes seem to be the other value. So that makes me believe that it's kind of it's a race. So the one that happens first is the one that's going to show up. And then if we go back in here and I turn this one off, but leave the other one on, and then go back to my trend, and I run this, now it's just a flat line. Why is it a flat line?
I think the counter has to be above 5.
Oh yeah, that's 0. Is it not above 5? Okay. So now there's 2 on, and I was mistaken before. So if we jump back to that trend, yeah, it's just, it kind of seems to be, you see the difference in those spikes as they scroll across. That looks like chaos, and I don't understand how that would be stored. But do you see what I mean? How quickly these are clearing? And we've got your 2.228 E6, and this one is 1.310724 E6. So it's not really stored anywhere, and only one is true at any time. So it likely has to do with scan cycles, scan rates, and which one kind of gets picked up. So I would guess it might scan and then go back and run the fault handling routine, and maybe it comes and picks this one up and then faults. So I know it doesn't store them per se. There is really only this major fault record, and since we're constantly clearing it, when it's these guys, when it's equal to one of those, it never really reaches anything else. If you wanted to store, let's say, the last so many values of the record, I would assume, like, I thought I'd developed code in the past that stored my last fault records based on a retentive timer. Bitwise rack stuff. Sorry. Coffee fault array pointer. So it looks like this is how that was done. So it looks like if you want to store additional fault data, you can use some indirect addressing, but in this one, it's not a counter. It's like the old school way of doing a counter of adding. This is actually subtracting the pointer from 1, and then shifting data around. So it looks like every time that there's a fault, it's doing a jump to move data around so you can have a number of the last faults that have happened. I think this code worked. This is the region of Waterloo, and I think this is working code. So you would have to build your data array and then figure out a way to force the fault scan to increment your data in a way where you could see what the last so many fault values were. And I have seen code, if not this exact code, but code like this working. Does that answer your question?
Yeah.
It's not, yeah, it's not as straightforward as, oh, go find this specific file. It's a pain in the butt. Oh, and I love it. That's it for the reading material. Okay, it's after 7. So let me see. So this is the lab. And if I can't get connected to this silly machine at this time, I'm going to say it's not going to work. So we go Econestoga, we download the file. So this file is in this week's data. In Allen Bradley Tips and Labs, download a random station file. I have done that, but it doesn't do me anything. Tips and Labs. These are just ACD files. Oh. Station 2. Okay, now we go to this link. So that's here. That's the same link as the other one. Open any PLC station file. Cambridge 8 remote access lab. So the only one is the open access lab. And we know that one does not have any physical PLCs. So here, yes, bear with me. Different. So this is now connecting into a physical machine there, is my understanding. Hideous. So yeah. Same thing happened on every other machine. So these are supposed, so this means that somebody's configured these, but this machine can't actually see them. Twenty to 21. Oh, you gotta be kidding me. So maybe no. Where were those? I saw some juniper. What the fuck? Like they're there. Sorry, so this piece of software is called Wireshark, and it's just when you turn it on, this is set up to automatically kind of capture and spit out all the information that hits the network port. So if you connect into a network and you don't know what's going on, you can actually see all the traffic that hits you to try to figure out what your IP address is. Sometimes you end up going to facilities where you don't know what's anything. So this is an example here, even without running. If you remember, we ran this to do like IP config. I'm 10.121.131.38. And then these sources are transmitting TCP requests on port I don't know, 222.222.2. But What? What? What is it? Oop. God. It pings. It should be that, but it's not. It doesn't. Uh, uh. Okay, I don't really want to waste too much time doing this. No, um, I don't know if this lab's going to work. You guys can try it out if you want. I don't know if it will. You can muck around with some of the minor faults and stuff with your emulator. The major faults don't all work. The emulator kind of faults funny sometimes. That's why it's better to do it on a physical machine. But by all means, if you wanted to try using this fault code on the emulator, go for it. Because I can't even get this silly lab to work. Like I am anyone who submits one, like everyone's gonna get 100% on it. Like it's not worth our time to try to stress over that because I can't get it to work. So I'm not expecting you guys to be able to figure that out as well. Like it's not fair to make you do that, in my opinion. And I'll try to talk to the other guys. Maybe I can get it working and set up a video and post that on the weekend or later this week. So is that fair? Everybody okay with that decision? Less work? Yeah. Anybody opposed? Oh, okay. So you guys don't even have access to the physical machines. Yeah, then there's no way you could be yeah, that's very frustrating. Well, then you're that's toast. Oh my goodness. I'm sorry, guys. I'm gonna write that down. Okay. No, I thought I downloaded it already. All right. No. You know. Visible. Project. Okay, so as promised, the project I've made available for you guys. So that should be all of the documents. 1, 2, 4. I keep doing that. Well, this transfers and opens. I'm just gonna use a watch. I'll be right back. Simple logic. So we are doing a donut machine. So the project, you're going to program a PLC system that manages the baking and filling portions of an automated donut machine. The donut machine renders a consistent edible product for mass distribution. Again, consider the functionality of the machine. The raw cooked dough to be baked enters the temperature controlled oven and is estimated by the temperature sensors upon exiting the oven to verify that the donut meets product expectations outlined below. Donuts that pass the quality control test are stored in a storage container before proceeding to the filling conveyor where the donuts are injected with a filling. Undercooked or overcooked donuts must be diverted to a waste bin. The amount of filling received by each donut must be strictly controlled to verify a consistent product. You are expected to draw from the supplementary materials provided from this course from the previous weeks when you're programming your system. So following the instructions in the process control narrative to complete your project, start early. I'm giving this, hey, Addie.
And sorry, before discussing about project, I just wanted to understand or confirm. So what is the plan for lab 5? Does it require that we submit something or?
No, I'm gonna give everybody, even those who don't attend, I'm just gonna give them perfect. So don't even worry about it. If you want to try and struggle, by all means, that is your choice to struggle for that. Everybody else who I'm just gonna give you perfect for it. Don't worry about it. Because I really don't think your guys have access to the machines, especially because you don't have access to the same physical machines I'm connecting to. There's just no way you can get at them. Like I'm very frustrated. I'm very frustrated, and the extent of the work that I would have to do to get you guys access to it, it seems insurmountable to me at this point, because I'm just very frustrated with the college.
Yeah, I just wanted to confirm that. Okay, thanks.
Aye. Any other questions about the lab? Everybody's okay with my decision to just kind of forego it. If you have questions about fault handling stuff, we can go over it again. Whatever you want. So program requirements: ensure the program's original structure, organizational structure, scan order, follows a meaningful order, place logic that relies on timers being done below the timer such that the timer is scanned first. Boolean addressing, ensure individual bits are only energized by one instruction in the program. Use AND logic at least twice, use OR logic at least once. Outside of ceiling applications, the use of ceiling logic in at least 2 separate applications. Avoid the use of latching logic within the program. Remember, if you have like alarm resets, if you have momentary or fixed push buttons and you want to use unlatches to latch something you've turned on in your application, your touch screen, if you want to unlatch it after a certain thing has happened, do that. Very common, but latches, not so common. Use at least one counter, one timer, use at least one shot, and use at least 2 math instructions: addition, subtraction, multiplication, division. Use the compute if you want. Use some compares, arrays, and some indirect addressing. The program requires the start button to be pressed to begin the sequence. Pressing the start button illuminates the button. The stop button is not lit. Pressing the stop button illuminates the button, and the start button is not lit. At least one unique feature is to be added to the PLC program using the existing IO found on the HMI. This is a complex feature, much like the last one. There's some expectations and tips later on. Cross-reference the IO table to interpret which inputs and outputs control the respective pieces of equipment. Fully understand the control narrative under the machine description and how the process is intended to operate. Write your program in the supplied template. So again, that simulation logic is there to make the machine run when you do things. If you find errors with it, I was running through this a bit. I didn't find some of the same errors I found with the last one. But if there is something that I catch or you guys catch, I will try to fix it, kind of similar to last time where I sent you a code update. Write your program and has to meet the criteria as done above. Add comments, descriptions, rung descriptions, and test your visual interface. So again, your visual interface is the touch screen. Demonstrate your functionality by creating a video like last time. However, everyone who did it last time, that was fine. Whether you use OBS or take the video with your cell phone, that was good. Demonstrate the functionality, processing at least 20 donuts. Describe it to me. What techniques you used, the use of the start button and the stop button in your program to run it, which lights indications are being used and what they represent, referenced instances of your unique feature. Your video should be no longer than 3 minutes. If you need more than 3 minutes, don't make it 10 minutes, but if it's like 3.5 minutes, I'm not docking your any time here, guys. Any questions so far? So again, rationale. So manage HMI and PLC simulation software using some of industry's best practices. Create a PLC program efficiently to control an industrial process. Apply programming features to PLC programs using best practices. The donuts here, again, move left to right. Uncooked dough. So this is the narrative. Uncooked dough is supplied to the system via conveyor A. Conveyor A passes under the commercial oven. Is used to bake the donuts. The commercial oven is designed with a maximum operating temperature of 450 degrees C that must not be exceeded. Due to the design of the burner, the commercial oven requires a minimum of 20 seconds between each burner enable program cycle. This is to let the coils cool and prevent damage to the unit. To begin the process, the system must follow a preheat phase where conveyor A does not run to supply uncooked dough to the system until the required oven operating temperature is reached to the desired to render the desired result. So the simulation logic is set up that this oven needs to heat up. So you need to play with that a bit. So play with your oven, your output, the burner on. You can see here, 430 will turn it on, but there's going to be some logic in there. After the operating temperature is reached, conveyor A will begin to run to supply uncooked dough to the system. As the uncooked dough passes underneath the heating elements of the commercial oven, the dough will begin to cook. The oven's temperature has a direct correlation to the rate at which the donuts will cook while passing through the oven. The conveyor will continuously run, acts as a constant time. The formed donuts will have variations in size, which will result in the unique temperatures upon leaving the oven. Dependent on their respective size, visually the donuts will appear the same. The automated system must be able to determine if the donuts have been cooked to the desired internal temperature to be accepted for downstream filling before proceeding downstream to the packaging process. This is determined by the donut temp sensor located after the oven. Use this sensor to determine if the donuts are undercooked, perfectly cooked, overcooked, or burnt. Perfectly cooked donuts will yield an internal temperature between the limits of 350 and 375 degrees C. Only perfectly cooked donuts may be accepted into the storage container for filling. The donut temperature sensor is used to measure the internal temperature of the donuts exiting the oven. Donuts that are not perfectly cooked must be diverted from the storage container to the waste bin. Undercooked, overcooked, or burnt state must be diverted to the waste bin. Donuts entering the storage container must be counted and displayed via the storage counter display located above the storage container equipment. The storage container must not exceed the manufacturer's recommended capacity of 50 donuts. Donuts exiting the storage container must be subtracted from the count to ensure the count indicates the updated current quantity of perfectly cooked donuts in the storage container. Within the storage container resides a specialty mechanism that is designed to discharge the donuts one by one from the storage container. The PLC is responsible for sending the command to the eject mechanism to allow the donuts to be ejected from the storage container and carried to the fill station via conveyor 2. Allow for at least 1 second between eject mechanism actuations. Upon the presence of the donut at the fill station, conveyor 2 must stop to allow the fill nozzle to lower and inject the donut with the respective selected filling supplied by the fill pumps. The desired filling must be selected using the filling selection output controls on each fill tank. The associated fill valves will open upon selection of the filling. Only one filling supply is permitted to the fill pump at any time. If no filling is selected while the pump is running, the pump may be damaged. Dry running the equipment is not permitted. Downstream packaging steps Require the donut flavors from the filling station to be staggered in groups of 6, with filling A to be selected first. The first batch of 6 donuts are to be filled via the filling nozzle supplied with filling A from the filling pump. The filling must then be swapped from filling A to filling B without running the filling pump. The subsequent batch of 6 donuts are then to be filled via the filling nozzle supplied with filling B from the filling pump. Upon completion of the 6 donuts receiving filling B, the selected filling needs to return to A without running the filling pump. The weight of the donuts is important to maintain product consistency. The donut yielded from the automated donut machine must be weighed by the fill station's weigh scale to ensure the filling provided to each donut is acceptable within weight tolerances before being released for packaging. A donut containing filling A must fall between the allowable weight tolerances of 30 grams to 32 grams. Donuts containing filling B must fall between the allowable weight tolerances of between 35 and 37. When either filling is spelled differently all over the place. When either filling tank A or filling tank B reaches 50% capacity, the PLC must indicate a low alarm via the HMI. All donuts processed and distributed must be counted and displayed on screen for operators. Donut entering and exiting the fill station weigh scale must not collide with the fill nozzle while moving. Acting as the operator, you must push the start button to start the program's automatic function. After pressing the start button light indication must be illuminated until the stop button is pressed. Pressing the stop button will stop the automatic mode, removing the illuminated indication on the start push button. The automatic sequence must resume where it left off when the start button is pressed. Provided are a series of inputs and outputs that will be used to control the pick and place machine. Additionally, please note that the design criteria, which outlines the concepts that you'll need to incorporate to the final functioning PLC program. Each concept successfully incorporated into the program will contribute towards the percentage of the total grade for the project. You're expected to draw from your knowledge from supplementary materials provided in the course materials when designing your PLC program. So here's your IO lists. You can see here, it's labeled the same as the other one that you guys had. So the list is good, but it's also on the screen for reference to help. Expectations and tips: ensure you understand the process before beginning. So print this out or write out in shorthand kind of how you'll move through. Write kind of even a timer, a counter for the different sections, especially when it's specific on different sensors that you need to use. Pay close attention to how those work. Don't go overboard programming the complexity. Straightforward programming is normally the best. Ensure timers are appropriately utilized to manage the donuts as they progress through the process. When brainstorming what to add for a unique feature, consider using the PBA, PBB light indications, as well as calculated values. Here are some ideas. So turn things on when certain milestones are hit. When donuts are present or moving on conveyor A, you can turn lights on. When the first 20 donuts have been filled, A or B can light up. You can indicate which fillings on by different lights. Use the available alarm indications to provide alarms in the HMI that would be indicated under abnormal or undesirable situations that an operator should be aware of. switch over here. Mhm. Yeah, no, neither of them. Doesn't. So one of the first things I would do would be fill in your descriptions for your IO. Save you from hopping around all over the place potentially. You know? Oh my goodness. That's annoying. So the donuts are running across. Although I suspect I haven't done anything. I suspect they're not cooked properly. They are underdone. But the oven's on, so it's heating up. Yeah, burnt. So the code's in there, like it said, it's going to burn these if they're underneath the temperature, the heat for too long. You got to watch where the thermostat is, where the heating element is. You can't speed this up. So you may need to heat the unit up, but potentially pulse this output on and off. Where are the rest of where are the inputs? All right, 42. Oh, just looking. Sorry, I'm just looking for the aliases they've set up. Yeah. Are there questions? Wastegate. 03. 313. Perfect. If you guys you've got access to the files. Anybody not have access to the files? Perfect. Yeah, if you've got questions, shoot them at me. I'm going to stop my sharing and stop recording for the moment.